In the previous class, we concluded with the concept of relative stability, that if I want my poles to be not in the left half plane, but left of -1, can I do that, or does my Routh-Hurwitz criterion give me an answer to that? The answer was yes. I could find out if the roots are to the left of -1, slightly to the right, or on the axis itself. But that may not necessarily be enough when I am handling design problems, right. So, what we will do today is to learn a technique called the root locus, which will tell me little more about relative stability, right. So, what is this root locus all about? So, when I design a system, so I want the system to be such that it meets the desired specifications. And if we go to our earlier lectures, the specifications were usually either in the transient response or in the steady state response. So, in the transient response, I wanted to speed up the response, but then I had a constraint of the overshoot. So, I wanted to speed up in such a way that I do not overshoot too much, and I also wanted the system to have very small or no steady state error at all. But before I do this, I always wanted that the system should first be stable. If it is stable, then I can look at performance, right. So, until now what we did, we just followed some analytical approach while we were doing the Routh-Hurwitz criterion. So, it does not provide, even though it gives me some information of relative stability, it does not give me too much information. I may need something more than just asking the question, do the roots lie to the left of -1 or left of -2 and so on, right. And it does not really help in choosing parameters in that way, right. It does not help in choosing a control where when I really want a little more fine tuning of the system parameters. Okay. So, if I look at a typical closed loop system like this, right, and I just ask a question, what happens if I change this gain? Okay. It could be from all values, possible values from -infinity to 0 and to +infinity. What happens to the system? Well, the Routh-Hurwitz does not really give me an exact answer to this question. Neither does it tell me any information about the settling time or the rise time, overshoot, or even the steady state error, right. So, for those things I need something little more sophisticated or little more in detail, right. Okay. So, let us see, are there any techniques like that, right. So, so what we will be interested is in the characteristic equation, the solutions of which will give me the location of poles of the closed loop system. So, we would like to know how the poles of the closed loop system vary by changing the gain k. Okay. So, this thing or the locus of the migration of the roots of the characteristic equation as the gain k varies is called the root locus techniques, introduced by W.R.R. Evans in his paper in 1948. So, what is this guy? This root locus is a technique, it is a graphical technique for sketching the locus of the roots of the characteristic equation as a certain design parameter. Here it's this gain k. It could be something else also, we will see how we deal with those. When this design parameter is varied, and these are the first two papers where this root locus was first introduced. Okay. So, let us not get into that at the moment, let us start with something very small, right. So, I start with a second order system. If I were just to draw it, I have in my forward transfer function 1 over s plus a, I have h of s is 1, a plus, a minus here, again all these usual things of r and c and so on, right. So, the characteristic equation of the system 1 plus g h equal to 0 gives me something like this. Okay. Now, the roots, okay, so I think I should also put a gain k here, right, another block. Okay. So, this will give me the characteristic equation in this way. So, the roots of this equation, second order equation, I have two roots minus a plus minus square root a square minus 4k over 2. Okay. So, let us analyze how these roots change and what are the two parameters here, a changes and k changes. Okay. So, for positive values of a, right, when a is greater than 0, minus a is always less than 0. Additionally, if k is also greater than 0, system is always stable, right, and because this guy, right, because and the roots of the system always lie in the left half. Okay. The relative stability now depends on the location of the roots, right. So, and then I could see that by varying k, which corresponds to my omega n in the second order analysis, this guy corresponds to 2 zeta omega n, dealing with the damping coefficient also, right. So, the desired transient response can be obtained by just changing this, maybe if the a is fixed, right. So, given a transfer function, a could be fixed. Okay. So, what happens? So, given a, there could be few cases because the roots of the characteristic equation depend on what is the sign of this guy. Okay. So, for case 1, when k is between 0 and a square by 4, the roots are distinct, right. I can just see very easily. When k equal to 0, the roots are at S1 equal to 0 and S2 equal to a. Okay. So, let us plot that for right. So, okay, just may plot it here. Yes. So, I start with k equal to 0, I am here, that is 0, and I am here, this is minus a in the S plane sigma and j omega, right. For k between 0 and a square by 4, right. So, this guy would be real in that case, right. So, the roots would be distinct. Okay. So, there will be somewhere, when I know that there will be distinct, they will just be real, this somewhere on this axis, could be here and wherever. But I know that stability is always maintained because a and k are positive. You do not even need to look at the route table, right. Here maybe you can just trivially see that the route condition is satisfied, and therefore, when we were doing the second order system analysis for given zeta and omega n, which was always positive, we never worried about stability because stability was very obvious in that case, right. You can now see that the route criterion satisfies this very trivially, and therefore, we were really never worried about stability. Okay. For k equal to a square by 4, this guy disappears and I have equal roots, minus a by 2 minus a by 2. Okay. So, let me just say that these are when k equal to 0, k equal to 0, and when k equal to a square by 4, well, this is at minus a over 2 occurs at k equal to a square over 4. Okay. So, when k changes from 0 till at least it reaches a square by 4, what I see that this guy starts moving here and this guy starts moving here until they both meet at this point, right, at a square, at k equal to a square over 2, and this point is just minus a over 2. Okay. Now, what happens after this, right. So, k was between 0 and a square by 4, well, I just say that these are somewhere here. I knew that they were somewhere on the real line, but now I know that when k equal to a4, they meet here. So, this guy travels here, this guy travels here. What happens for k being greater than a by 4? Well, the roots are complex and conjugate and given by this number. So, what you see that after k becomes greater than a by 4, a is given to us, right. So, this guy remains fixed. Okay. So, all the real parts will be at minus a by 2 and the complex part will follow this guy, which means, well, I am just so there will be all the real parts are a by 2 here and the complex parts will keep on changing. So, when k equal to a square by 4, I am here, and then I see that I am just moving around these lines and these lines. Okay. So, this is for k greater than a square by 4. Similarly here, k greater than a square by 4, and we know that if there is a root here, there will always be a root here, right, because of the nature of the system, right. So, the real part remains constant and the imaginary part varies as the gain k varies. Thus, the roots move along a vertical line, right, here 1 1, so they go this way and this way. So, what do we observe, right? So, as gain k for k equal to 0, I am just at the open loop poles. Okay. As k increases, both these guys meet up here and they again go away, right, to they'll just keep going till infinity. Okay. So, something nice is happening here, right. So, what information I used? I just used this guy, G is S, sorry, this is 1 over S plus A, right. I am not doing anything with the transfer with the characteristic equation now, and I am just interested in how this k times G and then now this will be the closed loop. Okay, I will not draw this out. This is, so I am just taking this information, right. This is this guy. Okay. So, what I observe for k equal to 0, I am at the open loop poles, and as k increases, these guys tend to move and they decide to move, they decide to meet here and then again separate. Okay. So, this is how, if I just play a very small video of this, right. So, this is how the roots will go. Okay, something okay, right. So, if I so again I will just play this again. K increases, so this guy will go and then for low values of k and then go small and then again come back to the position. Okay. So, this is how the roots will move. So, this guy will go here and move this direction, this guy will go here and move this direction, right. Okay. So, what did we know, what did we see here, that so the root locus, it indicates the manner in which the closed loop zeros and poles move, so that the response meets some specifications. So, my specifications are usually in terms of zeta and omega n, and these specifications usually translate to locations of poles. So, there could be some zeta and omega n which would be maybe satisfied by k equal to a square by 4 plus 1, right, then I would know, right. So, I will exactly know where the roots are, maybe somewhere here and somewhere here, right, and then I would actually exactly know what should be the value of k such that my closed loop pole satisfy some desired specifications or some desired performance criteria. Okay. So, I would know how to modify the gain k such that my performance is met, and performance is usually mapped to some pole locations. Okay. And I am just doing this only with the knowledge of this guy, right. I started with S, the open loop poles, S at 0, S at minus a, and I am just now increasing the gain k. We will see how we'll formalize this a little later. So, just by looking at these two, I start with the open loop poles, and these are all the closed loop things now, right. As k increases, I am already in the closed loop, right, and then how the closed loop poles are modified starting from the open loop poles. So, I just need to know how the open loop system looks like, and I can just do a good study of the closed loop system. So, I do not really need to compute the closed loop poles and then I analyze things and so on, right. So, how are poles related to pole locations related to the performance? Well, we analyzed this while we were doing first order systems. So, just say if for different values of poles at S1 I will have a faster response, S2 slightly slower, and the slowest will be for S3, right. So, this is like how the location of poles influence the performance. This we did while we were doing analysis of first order systems. Okay. Now, in general, so the first order systems was very easy, right. So, all the poles are on the real line, then okay, based on their location I would determine how are they fast, are they slow, the slowest would be here and the fastest would be very further away from the origin. Okay. However, for second order systems there were little more details, right. We started, well, we had undamped systems where we had the maximum overshoot, the settling time was infinity. Then we had the case of underdamped systems where we quantified or we defined underdamped nature in terms of zeta, right, and then we had also when the system was undamped, the frequency of oscillation was omega n. For sigma equal to 1, the system was critically damped, and then we also had the notion of over damped system where this zeta was greater than 1. Okay. So, if I just look at the poles, right, typically, well, I am just looking at solution to this equation, right, s square plus 2 zeta omega n s plus omega n square. Okay. So, if I just look at the underdamped case, my roots were minus zeta omega n plus minus j omega n square root 1 minus zeta square. So, this is for zeta less than 1 if we remember it properly, and this guy I said this is omega d. Okay. So, this is the real part here. So, if I just take a complex conjugate pair, right, P1 and P2, the real part, this distance would be, this will be at minus zeta omega n, and then this guy would be omega d, this distance. Omega d is omega n square root 1 minus zeta square, right, just like, so this is a right angle triangle, and I could say that this omega n is just square root of this guy plus this guy, right, from the Pythagoras theorem. Okay. Now something else, right. So, this is what we also call as the omega d, right. Okay. Now look at this guy theta, right, and if I say how does cos of theta look like? Cos of theta is, okay, this guy zeta omega n over omega n is just zeta, right. Okay. So, from this cos of theta is zeta, and therefore, theta is cos inverse of zeta. Okay. So, let us look at this, right. So, if I am at this point, theta remains the same whereas omega n changes, right. If I go here, if theta is the same, then zeta is the same. Okay. Now, if I go from here till here, this distance which is omega n changes, but cos of theta still remains the same, right. Slightly here also, if I go from here till here, what happens? My zeta remains the same because theta is the same, right, if I am just moving along this line, right, and then omega n changes, right, for some given zeta. So, all these lines are lines which I call as constant zeta lines. So, I can go here, right, if I just take any arbitrary line here, right, for which a theta would be fixed, if I move along this line, right, what happens is my theta is fixed whereas omega n changes. Okay. So, this behavior could be seen from zeta equal to 0, I am here, I keep on increasing zeta, and there are all these lines are the lines for which the zeta remains constant. So, at this point you will have different omega n, this point different omega n, but the zeta here is same, similarly on the other side. Okay. So, these are all constant zeta lines, or we just say how the locus of the poles look like for constant zeta. Okay. Now, let me keep omega n fixed and keep moving, right, and I just want to vary theta. So, what will I do where omega n is fixed, and I just move around some semicircles. I do not want to do a circle because I do not want to go into the unstable region. So, if you look at this guy over here, omega n is same, omega n is same, omega n is same, but each of these will have different zeta, right. This will have a different angle, this will have a different angle, and this will have a different angle. So, if I keep on moving omega n, then I just move, I am just moving along a circle. And this guy also, since all poles exist in complex conjugate pairs, so this guy will also moves just according to how the omega n varies. So, you just have some semicircles here. So, there is a pole here, there is also a pole here, and this will correspond to certain zeta. If I go here, this pole will move here, and this pole will move here, right, the complex conjugate, but then the zeta will move. So, these are semicircles where omega n is constant and zeta is changing. These are lines where zeta is constant and omega n is changing, right. Okay. What is What is the importance of this? Then I say, well, design something such that zeta is some number and omega n is also some number. Say zeta is say 45 degrees and omega n is 1. Okay. So, I have this constant omega n circles, and then I just draw a line of say zeta or the theta being 45 degrees. So, I just draw a line from here till here, and if say this is omega n equal to 1, then my pole should be here. Okay. So, if I have, again I will repeat, if I want a design specification where zeta should be say some number which corresponds to angle of 45 degrees, given theta I can always compute zeta, right, and then add a certain omega, let us say this is 1. So, I just find these two lines. So, this is my zeta, right, and then this is my omega n equal to 1, and the point where they intersect is where I want my closed loop poles to lie. And this I know how, from the previous example, that I could vary these closed loop poles just by varying the gain. Now, I will just investigate, is there any gain which will do me this? Now, how do I test, right? So, that is exactly what we will study in the root locus case. Okay. So, this was just a little example, right, and now we will see how we can generalize this, right. Do the roots, so what we saw that the roots were traveling towards each other, they meet and then they go away. Do they always meet? And if they meet, do they again have to go, do they have to go to the imaginary axis, or they could possibly just stay over there? There was no 0 in our example, right, it was just s 1 over s plus a. What happens if there are zeros in the system, right? So, all these things we will try to analyze a little more. This will lead us to some conditions on the root locus, right. So, all these rules is what we will do in our next lecture. Thank you.